All right, projectile motion. If you're doing NCEA physics, you've seen these problems, right? They can look super intimidating, but I promise you, by the end of this, you're going to have the one secret that just makes them all click.
I mean, you look at a path like this perfect curve, and your brain just kind of goes into overdrive, right? You're thinking, wow, that's got to be some seriously tough math to track something moving sideways and up and down at the same time. And look, that's a totally normal reaction. But what if that curve is kind of an illusion? What if the secret isn't about solving one really hard problem, but about solving two super simple problems that just happen to be running on the same clock? Well, that is the secret we are going to unlock.
Okay, so to get there, we gotta lay down some ground rules first. Let's get really clear on what we're talking about when we say projectile, at least in the world of NCEA physics.
So think about it. A rugby ball after it's been kicked, a rock you throw off a cliff, even a cannonball. They're all projectiles. And the one thing they all have in common, after that initial push or kick or whatever, the only thing acting on them is gravity. That's it. We're going to completely ignore stuff like engines or any extra pushes, and this is a big one, we're ignoring air resistance.
And you know what? These three assumptions, they are your absolute best friends in an exam. Seriously, no air resistance, that just means nothing is slowing our object down sideways. Easy. Constant gravity, that good old 9.8 meters per second squared, gives us a number we can always count on for the up and down stuff. And the whole flat earth thing, well, that just keeps the math from getting crazy. Simple as that.
Okay, you ready? This next part, this is it. This is the single most important idea in this entire topic. I'm not kidding. If you really get this one thing, you've pretty much cracked projectile motion.
Here it is, the golden rule. The horizontal motion and the vertical motion are completely 100% independent of each other. What an object is doing sideways has zero effect on what it's doing up and down, and what it's doing up and down has zero effect on what it's doing sideways. It's like they're in two totally separate universes that just happen to share a stopwatch.
And this just lays it out so perfectly. Check out the horizontal side. No forces, zero acceleration. It's just cruising along at a steady speed. I mean, that's about the simplest kind of motion you can get, right? Now, look at the vertical side. You've got one force, gravity, and that gives you one constant acceleration pulling it downwards. That's it.
And that's the whole principle right there, the independence of motion. This is basically our permission slip to take that big, scary-looking curve and just split it. We break it down into a super simple sideways cruise and a super simple up and down fall. Two easy problems instead of one hard one.
Okay, so we've got the golden rule locked in. Great. But how do we actually use it? Well, let's build the practical step-by-step toolkit that you can use every single time, no matter what problem they throw at you.
This four-step plan, this is your secret weapon. For real. Number 1, always draw a quick sketch. 2, split your starting velocity into its horizontal x and vertical y bits, using a little bit of trig. 3, set up that 2-column table to keep everything separate. And 4, the big one, go hunting for the one thing that connects both columns, time.
And this table is your roadmap for the whole problem. Just look at it. The acceleration on the horizontal side, always 0. The acceleration on the vertical side, always that negative 9.8. And see that little t for time? It's the only thing that shows up on both sides. It's the bridge between the two worlds. And trust me, keeping things split up like this will stop you from making the #1 mistake pretty much everyone makes.
All right, enough talk. Let's actually put this whole toolkit to the test. We're going to tackle a classic NCEA-style question, the old ball rolling off a table problem, and you'll see just how simple this method makes it.
Okay, so first things first, we set up our two columns. Horizontally, we know its starting speed, and we know the acceleration is 0. Vertically, well, right at the moment it leaves the table, it's not going up or down, right? So its initial vertical speed is 0. But we do know its vertical acceleration is negative 9.8, and we also know how high the table is.
So now we hunt for time. Just look at that vertical column. We've got the distance it falls, we've got its starting vertical speed, and we've got the acceleration. Hey, with those three things, we can just plug them into one of our kinematics equations and solve for t. Boom. That tells us exactly how long the ball is in the air.
And here it comes. This is the magic step. As soon as we have that time from the vertical side, we just pick it up and carry it over to the horizontal column. And since the horizontal math is super easy, just distance equals speed times time, we can plug in our time and find the range. Just like that. Problem solved. See? You've got the method down. But now, let's talk about the exam itself. We need to make sure you don't fall for any of the common traps that can really cost you easy marks.
Okay, so listen up. You really want to burn these into your brain. First, acceleration is never zero at the top. Gravity is always pulling, always. Second, once it's launched, there is no forward force pushing it. None. Also, don't you dare mix up your columns. Never use gravity on the horizontal side. And remember your signs. Down is usually negative. Lastly, be careful with shortcuts, especially if the ground isn't level. Seriously, if you can just watch out for these 5 things, you're going to be golden.
And that's really the whole thing, isn't it? That's the secret. The next time you look at one of those intimidating projectile paths, don't see a complex curve. I want you to see 2 things at once: a simple, steady cruise in a straight line, and a simple fall straight down. Because once you see it like that, you'll never be able to unsee it, and every problem becomes solvable.